Solutions and hosted by 3D Metal Printing Magazine. My name is Brad Kuvan. I'm the publisher and editor of 3D Metal Printing Magazine, and I'm pleased to serve as your moderator today. Before we get started, just a few notes about today's GoToMeeting. This meeting is being recorded for archiving, and the recorded event will be posted to our website within the next few days. We'll let you know via email when that recorded webinar is available for viewing online and for sharing. Also, all participants in this meeting are in listen-only mode, so the speaker and other listeners will not be able to hear any audio from your site during the program. However, you do have the ability to communicate with us throughout the program by submitting your questions and comments using the question box, which is located on that right-hand control panel on your GoToMeeting screen. So you'll simply open that question box and type your question to an organizer as selected from the drop-down menu. You'll also use that same question panel to ask questions of our speaker at the end of his presentation. We should have plenty of time at the end of the presentation to take your questions. So now it's time to begin today's webinar. Our speaker this afternoon is Kyle Adams. Kyle is an application specialist at SLM Solutions. Kyle is going to discuss with us today the types of parts, features, and geometries that are best suited to be optimized for additive manufacturing. He'll also outline the initial steps manufacturers can take when they're implementing an additive manufacturing strategy. So without further ado, please welcome Kyle Adams.
Okay, thank you, Brad. As Brad said, this is a webinar on selecting parts for additive manufacturing. Just going to start here. So my name is Kyle Adams. I'm an application specialist with SLM Solutions. Been at the company for 3 years here in October. And SLM Solutions, we provide the metal 3D printer, so we are a machine provider. What we're going to go over here is the 7 attributes for selecting a metal additive part. And we're going to go over some examples in a summary. So a little bit of introduction to SLM Solutions. This is our new building. We've just opened, or have our grand opening next week. SLM Solutions was started back in 2011 as MTT. It was renamed SLM Solutions. It's headquartered in Lübeck, Germany here. We have 6 sales offices around the world with about 360 employees in sales, engineering, and manufacturing. We are the first company to process titanium and aluminum in a powder bed process. So this is the office for SLM Solutions North America. We're a subsidiary of SLM Group, founded in 2011. We have about 30 employees and well over 100 installs in the continental United States, and also including a few in Canada. We have customer support. So as you can see on the bottom right-hand screen, we have a in-house lab. So we currently have 2 280s, 125, and an SLM 500. We also have customer service and field service. So we have our own warehouse, field service engineers. We provide solution development, so material development, process development, and then also any service with the machines provided through the U.S. office. These are the 3 machines that we provide right now. SLM 125, as the name suggests, it's a 125 millimeter cube. Has a single 400-watt optic in it. And then we have the SLM 280 2.0. This is an improvement of the original SLM 280. It's got a 280 by 280 by 365 build envelope. You can get that with either a single optic or a twin optic. That's 2 200s or 2 700-watt fiber lasers. SLM Solutions was the first company to introduce the twin optic setup, and then we improved on that with the SLM 500, which is up to a quad optic system. Again, with up to 4 700-watt lasers. The builded chamber on that is 500 by 280 by 365. This is a production-based system. So these are the, we operate in a few key industries: automotive, aerospace, energy, tooling, and healthcare. Our big one right now is obviously aerospace and energy, based on just the initial entry cost of metal additive in general. Automotive is a very much emerging market right now, and we're going to show some examples here later on of some automotive applications that have come to light in the past few years. It's a very interesting market because there's a lot of stuff that can be improved in the automotive industry. These are just a few parts that we have that are made right now in additive, and these are all actual applications. The top left piece is a wing bracket for airplane, and just a bunch of different little applications. We're going to revisit this in the future, and maybe, hopefully by the end of this presentation, everybody online can understand why each one of these parts is a good fit for metal additive due to features, production number, complexity, and so on. So some of the advantages of the SLM technology, the direct advantages are there's freedom of geometry, there's a much reduced build time in relation to casting. Part cost for small production runs is much lower in relation to casting. Getting castings can cost up to a couple $100,000, especially on short turnaround in metal additive. You can run them same day, same time. Part properties, these parts are stronger than castings. And prototyping, so we can do quick iteration on prototyping, you know, from design to build in a matter of days or hours versus waiting months or so on to get a casting made or a forging or anything else done. And some of the indirect benefits, we have increased speed and flexibility because of, you know, the ability to build the part is required out of nothing. We can reduce weight by doing lightweighting structures, internal geometries, and lattice structures that would not be able to traditionally be done in a traditional manufacturing sense. Including things like conformal cooling and aircraft parts, engine parts. These are great applications for additive due to the increased cooling capacities that can be added into them and the increased lightweight properties that we can put into each part, and the material savings. So all our material is completely reusable. Each build, you get about 98% reusability of the material that's unwelded. So versus the traditional machining out of a block, you are able to reuse a lot of different, lot of material. So we're going to go a little bit over the process of the SLM machine. So right here we see a SLM 500 building with 4 700-watt lasers. What you just saw there was the recoder traveling from the back to the front. What it's doing is laying down a powder bed, thin layer of powder, and then you just saw the lasers here welding the part. The recoder bed is going to travel back. One of the benefits of the SLM is it's bidirectional recoding. So every time the recoder moves, we're laying down a new layer of powder, and we're able to build about 40% faster just based on that. The laser that you're seeing moving so fast right now, it's actually about a 75 micron spot that is moving at about a meter a second to weld. Currently, we're doing 30 micron layer thicknesses. So as this part is building, the platform is moving down 30 microns at a time. And you can see that, you know, each optic, all 4 optics are all working on the parts at the same time. This increases our productivity on the SLM system over a traditional single optic system. Now, we're going to get into the 7 attributes here of selecting a part for metal additive. So the 7 attributes, and I included 7 attributes with 7 questions to ask yourself when trying to select a part. So size, does the part physically fit inside of a system? Is the part, you know, the right size? Is it too large, or some features may be too small? I said there's a 75 micron spot size. That may be, if you have a feature smaller than that, then it might be too small. Material, does it weld? This is essentially a glorified welding process, so we need to know the material welds. Economics, is there value? do we want to build this part because it's going to save you money, or do you want to build this part because it's cool and you just need to get into additive? So that's a question we need to ask. Performance. Is the material being made out of the SLM system meet the performance values of the requirements of the part that you need? Qualification. Is it yours? Are you the design owner of this part? Does this part require to be made in additive, or does it not? And design, will it work? We like to say that we can print anything, it's just some parts just don't make sense. We can get into that a little bit later. And then post-processing, is it painful? So this isn't a put file in, get part out. There is a lot of post-processing work involved. And does the post-processing make this, cost prohibitive? So, does it fit? Right here we have the standard SLM 280 build plate. So this build plate is actually 278 millimeters by 278 millimeters. As you can see, also the bolt holes in all four corners are there, so the plate is held down to the subplate as the plate moves. This is lost area, so your part may actually be 280 millimeters, and it might not fit onto a build plate based on geometry and positioning of the part. So when we say 280 by 280, yes, the build cylinder is 280 millimeters by 200 millimeters, but there is some smaller tolerances and, of course, the ability for clearing out bolt holes here that we need to take into consideration when placing a part. Material, does it weld? So SLM process is really a glorified welding process. The same rules of weldability apply, and it means that some common engineering metals cannot be used, such as 775 aluminum or some of the nickel-based superalloys. That being said, there's usually an alternative to these materials, and we can always look at, if you were based in 7075 aluminum, we can look at alternatives to cover that material and the properties you're trying to reach. Also, because the SLM process uses powder, you have to have a source for high quality powder. This is a top-down gravity fed system, so the powder needs to be spherical, it needs to flow, and it also needs to be dry. And sometimes the preferred powder might just not be available. Here are some of the materials. So when metal AM started, we started using some of the same alloys that were already being used in casting and some of the ready available materials in powder form. So what you see here is we have 8 of the main materials that we use: AL Si10Mg for the aluminum, cobalt chrome for medical and dental applications, the 2 Inconels, Inconel 625 and Inconel 718. Titanium, we use Ti64, and then for tool steels, 12709, 316, and then for precipitation hardness steel, we use the 174pH. Now, for about 80 to 90% of the jobs, these are the materials we use every day in the lab, which I run. That being said, there's always new materials being developed. We have an open system, so that allows us to take any material that is developed, and as long as it meets specs for flowability and powder size, we can run it through the system, create a set of parameters for it, and then be able to continue on and develop a case for that new material. Next one, economics. Is there value for us in our system, or for you to purchase this system with the part that you want to produce? So what you see here is an SLM part cost illustrator. There's a lot of back-end calculations onto here, but this helps us determine the value and part cost of a specific part you want to build. This is a very well understood process, and because we can understand very closely the build times and the machine time going into this, the amount of material used, the amount of electricity, argon or inert gas, and everything else going into operating and building a part, including man hours, we can understand within a very, very accurate number, how much is this part going to cost you? And we can do that, and we can compare that to a traditional manufacturing sense. One of the rules of thumb is that one SLM machine will produce about a ton of material a year. So we need to understand how much you are looking to produce, or how much is being looked to produce, to understand how many machines would be needed to produce the required amount of material. So this is kind of 5,000 kilograms a year given by the design. So 5,000 kilograms would be about 5 machines, 5 SLM machines would be needed. You know, for example, this is one of the SLM uses. So what this is called a stealth key. It is a highly secure physical key. So it's a very small part. You know, it's an actual physical hand key and fits on your keychain. But we can produce this build plate right here, built on an SLM 500, produces 1,083 stealth keys in a single build. So the number of keys required is very high, but the number that we can pack onto a plate and the number we can build in a very short period of time is also very high, so that we're able to meet the needs of this particular application extremely well. And you can see here in the SLM 500, it's using all 4 optics working at the same time to produce this material as fast as possible. Another great application, high value, high performance materials. So this is just a couple of pictures of a bunch of different applications that we use, such as transmission housings, or you see there's a cylinder head here in the top middle, which the cylinder head traditionally is cast with very direct cooling lines, but because of the SLM process, we're able to, instead of doing direct straight cooling lines, we're able to do conformal cooling and create a better cooling effect on the cylinder head itself. Turbo housings, you know, tire molds, and then of course you see in the middle here, this is actually a great showpiece. This is the Bugatti brake caliper, which we'll go into a little bit more detail later on. This is produced in titanium. It saves about 7 to 14 pounds it's 7 pounds per side, so about 14 pounds per axle front and rear, so of unsprung weight. So this is a very great use of the SLM process. It's a very large part. We'll show it to you a little bit later here. Next step is performance. So we're going to get into, does the performance of the material we make meet the requirements of the part you're trying to produce? So main point here is this is not the same material as cast, and it's not the same as forged. So, and it's not the same as MIM either. So this is its own technology, and it's got its own unique microstructure. This here is actually a close-up picture of the microstructure of material as printed. So you can see all the waves throughout this. These are layers upon layers of weld bead laid down to produce the part. You can also see the borders and the fill contours inside there. And also right there on the side, you can see there's some porosity. So the SLM process says that it's 99.9 to 99.98% dense. So there's always the chance of some porosities, and this is going to have to be taken into consideration. So these are some of the important material part properties that are taken when we're considering parts. So surface roughness. We got about 6 microns of surface roughness from as printed material. Obviously, due to post-processing, this can be improved based on the application, but out of the machine, it's about 6 microns. As far as strength goes, in tensile strength, we're about 2 to 4% lower than wrought material. So still very strong, stronger than cast, but not quite, you know, top strongest material. Accuracy. So this is accuracy across the machine as far as part accuracy. We can hold anywhere between 50 to 100 microns based on calibration and the tolerances set up of the part that you're trying to produce. So we are not going to get a direct one-to-one part perfectly sized every single time. There's about a 50 micron tolerance there, and that has to do with the next thing, stress. So the powder bed is preheated to up to 200 degrees C, but since it's a welding process and there's miles upon miles of weld bead being laid down, there's a lot of stress buildup during the production of these parts. Densities. So we can have a 99.8% density. We can improve that. We have reached 100% density. It's just the amount of control of the process that goes in, and also the application needed. Does it need to be as dense as we need it to be, or in other applications, sometimes less dense, in fact, even porous material can be made for certain things such as replacement to sintered filters and so on. And then as far as hardness goes, out of the machine and including, you know, heat treat, HIP, and other post-processing, we're a few points lower than wrought material. So metal AM can always be considered a casting replacement because we're always going to be stronger, but we might not be a forging or a billet replacement. Some design changes may need to be made directly out of the box. Next attribute here is qualification. Is it yours? And I know this sounds like a silly question, but we do run into this quite often, is this part made to print? If the print does not call, so the design does not call for the part to be made on SLM technique, you won't be able to make the part using SLM. If it requires the part to be forged, the part will need to be forged. If the call out requires the part to meet an AMS spec, and the AMS spec refers to a part that was made by casting, we cannot use additive. So this is, we need to get design authority. We need to make sure that the parts that we're selecting meet specifications from the designer through to the vendor, all the way down to the end use supplier, and all the specifications that are required with that part is, are we meeting the specs of the parts that need to be made? And do we have the right to make this part in metal additive? Design, will it work? So, metal powder bed has a couple unique challenges as far as supporting, mitigating stress from the welding process and preventing voids that would otherwise trap unwelded powder. So if we're looking to replace a subassembly that may have a completely closed chamber, we won't be able to produce that metal additive because of our process. That chamber would be then full of powder. So we're going to have to design a way to remove that powder from this system. And also optimizing, you can see here there's two separate parts, and the part on the left, though it looks, you know, organic and lightweighted, everything you see here is support material besides the base part itself, and all that support material needs to be removed for this part to be usable. So designing parts that are able to be built without support or minimizing support is a very, very big part of what we're doing, and the support does not break off. It is like material. It's the exact same material as the part is. So it's non-dissolvable. We're not going to be able to just put it in a solution and wipe all the support away. If we could do that, whoever came out with that process would be able to retire tomorrow. So we're going to have a little video here. This is from Dassault Systems. So what it's going to do is it's going to show a bracket that's right here being designed, and it's going to go through a couple different processes to show the best way to optimize this bracket for a couple different manufacturing techniques. So we're going to obviously select the load ratings, or load areas, and put in what needs to be done to this bracket, and then we're going to show the best way to design this bracket for additive manufacturing, casting, and milling. And so you can see there are some small differences here, whereas the part where the casting has a very big, part of the casting has a very big void right here that would otherwise need to be supported in a metal additive process, whereas the metal additive part here, that support area, the area that needed supporting, was actually designed in so this part could be built without supports in those key areas. And the milling, everything is very straight. There's somewhat organic, but this is all designed for traditional milling and manufacturing techniques. So these are just some of the design changes that need to be made for metal additive. Post-processing. So this is one of the bigger things to consider when building parts. Everything can be put into an SLM system and be built. It just depends on how much support is required and how much time afterwards it's going to take to clean it up. So what needs to be done during post-processing? There's a few things. Quality verification. Does the part need to be CT scanned? Is there a dimensional analysis that needs to be taken care of? Stress relief. So like I said, and I said before, this is a welding process, so we need to relieve the stress in the part itself before we move it from the plate. Does the part need to be HIPed, or hot isostatic pressing? So a lot of aerospace spec calls for hot isostatic pressing. Also heat treatment. What is the heat treatment required for this part? How are we going to remove the part from the plate? How are we going to remove the supports? And how are we going to finish this part once all that is done so that the part is ready to go for its application? You can see here on the right-hand side, there's the part on the top and bottom. On the far right, this part is made completely support-free. It is a part that is built, cut off the plate, and is finished. There's no support required. The larger picture and the part in the middle here, this is a part that was designed, it was optimized. This is actually just a scale model of the part needed to be made, but there's a lot of support material inside there that need to be removed. And I can tell you from experience, because I was the one who cleaned this, this takes hours upon hours of cleaning and removing the support material. So the first step, quality verification. So X-ray computed topography or micro CT, what we're doing here is we're actually looking at voids inside of the part. So this is without cutting the part open, without having to create density samples. We can take this part, scan it, and we can see all the voids inside this piece. So this top picture here on the left-hand side, you can see all those little triangles and blue and green and red dots. Those are voids what's inside of an additively produced part. Also, micro CT allows us to fairly accurate measure internal geometry, something that we would not be able to get a touch probe or a visual indication on. So in the bottom left, or bottom right, you can see there's internal channels within a part. And so within those channels, we can measure the size of those channels with a micro CT to see exactly if those channels are the right size that we need to produce the flow characteristics for this particular part. Also, CMM inspection. So in the top right, we have a handheld CMM. This part is very useful for scaling material and checking outside dimensional accuracy of parts. And in the bottom left-hand corner here, we have a Keyence VX series microscope. We use this for looking at density samples and metallography samples. So the CT scanner is great, but at the end of the day, it's always good, especially when developing new materials, to cut it open and take a look inside, because we get to see quite a bit of how the melt pools are being formed. Depending on etching, we can see the microstructure of the metal, and we can see the grain growth, and we can understand more what's going on inside of the process, and really take a look at slowing down what we're actually seeing inside of the machine with the laser moving so fast. stress relief. So I'm gonna need a little bit of this once I'm done with this presentation, but stress relief, we have an argon furnace here on the left-hand side, and we have on the right-hand side a vacuum furnace. So argon blanketed furnaces are great for doing stress relief and heat treat for most common materials, steels, Inconels, aluminum. When we move into aerospace spec stuff or titanium or Inconels where oxygen inclusion is a major concern, we're going to move into a vacuum furnace. So that vacuum furnace is going to be pulled down to, a complete vacuum. It's going to be heated and run. And there are specs on most heat treats for most materials already. So this is something that we understand very well. We understand how we want the metal to react in the end and what type of heat treat and post-processing needs to be done from the as printed material to reach the specs that the part is required. Another thing is hot isostatic pressing. HIP applies high pressure and high heat to the workpiece or to the part in question. So what we're going to do is we're not actually melting the material, but we're going to get it to a point where it's so soft and the pressure is so high that all the voids, like we can see here on the right, will be closed up. So hipping processes are almost 100% required in any aerospace spec. It's something that it's a catch-all, it's a fail-safe. If there's any type of void inside of the part that's produced, a hot isostatic press will more often than not close up any of those voids and allow it to be a fully dense material and to meet specification. Next is removal from plate. So there's three types of ways that we can move something from a plate. Wire EDM, which is a very clean, very straight process. It's also a very high cost process. With a wire EDM, a lot of the times we're using a wire EDM if we want to weld and extrude a part directly to the plate, and we want to cut through a large amount of solid material with a very flat bottom surface. We can use a wire EDM system to cut through these plates. So you can see in the top left that spark on the side. This is cutting up this brake caliper here with wire EDM. More traditionally, bandsaws. Bandsaws work great for cutting off support material. The support material is very thin material, and cutting it off from a plate using a bandsaw. This is actually the bandsaw that SLM Solutions US has, and we use every day to cut our parts off of the plate. It doesn't need to be that big. We spec'd ours for our largest machine, the SLM 500, so we do have a very large system. And then the third one here, which I'm going to show you a video again, is just breaking parts off of a plate. So the part in question that's being shown here is actually a perfectly designed piece where there's no support and no bandsaw or EDM needed. So we play this video. These parts are snapped right off the plate. So that's a very well-designed part. That is the perfectly designed piece where we can break a part right off of a plate with our bare hands and then move on to the other post-processing techniques. What we see here is this is actually material being removed. So there is no magic bullet to remove material. It has to be done by hand right now. So you can see our shop operator at SLM's US. He's removing this material off of aluminum. So this is still a fairly fragile material in aluminum, and you can see that he's still struggling to break this material off. Now imagine if this was titanium or Inconel or anything of that nature. That material would be a lot harder to remove. Not just hand tools snapping this off, but we're talking about using air chisels or die grinders, tools like that to remove some of this material. And you see the material does break off. Unfortunately, once this material is welded, it is not reusable. This is a one-time use material, but you can see here that the base part is still very strong, holding together while we're able to break the support material off. And there's a fine line of supporting material where we want it to be strong enough to hold the part down, while at the same time being easy enough to remove after the process. Surface finishing. So what type of surface finish do we need? Is an as-printed surface good, or do we need this surface polished for flow characteristics, or what else needs to be done? So electropolishing, grit blasting are great processes to kind of improve the surface roughness of a part. You can see on the right, this is an as-printed part on the left, and a very rough surface finish. So, you know, 50, it's a RA of 7.9. So this is a D-Light system. We have used the D-Light system in the past. It's a very nice system to use, but it has basically dry electropolishing, and it's gone through and it's reduced the RA down to below 2 across the entire part, while still maintaining most fine features. So that's another thing, is fine features, maybe 90-degree edges and things like that, might be knocked away during a surface polishing or electropolishing technique, and we need to know if those 90-degree or fine, sharp features need to be maintained throughout the process. So I've assembled 2 examples here that go through our entire SLM process, and afterwards we're going to go through the 7 attributes and try to identify each one within these 2 examples here to see that these are good parts. So this is the roof bracket for the BMW i8. Right here, it's being produced in the SLM 500. You can see that there's enough for in production. The part was broken right off. And here it is in an end function, the actual in use. You can see the bracket. So, as the video plays, size. Does it fit? Yes. We can fit many of these on a plate. We can fit a lot of these on a plate, so the size is good. Does it weld? Yes. This is an aluminum bracket. It holds up a very lightweight piece. So material, does it weld? Yes. Economics, is there value? The BMW i8 Roadster is a very low production vehicle. So this is a fairly specialized part that only needs 2 per vehicle on a very specialized vehicle. Economics makes sense, absolutely. Performance, is it met? So the aluminum, very light material. The part that's holding up is also very light. So there's not a lot of stress or weight being held up on this part. So yes, the performance is met. Qualifications. This is go without saying. BMW designed this. They designed this bracket directly for the metal additive process. Yes, it is theirs. Design, will it work? Well, it's in production and you could buy one today, so yes. And post-processing, is it painful? The answer is no. Post-processing on this is to break it off the plate. I believe there's 1 or 2 small clearance for bolt holes that need to be machined into, and that's it. It's a very easy part. Is it painful? Check. So it's not very painful process. Great application here, great piece. Our next example here. So this is an SLM 500 quad laser building titanium right now. This is the part being removed from the build cylinder. You can see the powder just falls away. Everything that's not welded is just loose powder, can be brushed off and removed to be reused. So this is the brake caliper. Now it's in a wire EDM. It's being cut off the plate. And here is the finished part. So, size. Does it fit? Yes. It's a very large part. It's actually the largest brake caliper on a vehicle ever, production vehicle ever. But yes, it does fit. You can print 1 per build plate. Material. This is Ti 6.4. So these are traditionally single piece, either billet or cast aluminum. These are built on titanium, so lighter weight, much stronger. Does it weld? Yeah, Ti 6.4 does weld, so the material does work. Economics, is there value? Seeing as this is a almost $3 million vehicle, and really a technology demonstrator is a vehicle itself for Bugatti, yes, there is value for them to print this part. Obviously, the first implementation of metal additive brakes in automotive. Performance, is it met? This brake caliper has been tested. It is going into production. The titanium is strong enough to hold up to the braking forces of driving well over 250 miles an hour. Absolutely. Qualifications, again, yes, it is designed by Bugatti, it's for Bugatti, it is theirs, they do own it. Design, will it work? So there's a lot of support, but it was fairly easy to remove, and it was designed organically enough that the support comes off fairly easily. And post-processing, continuing on. Is it painful? Between the wire EDM and the support removal, obviously much more support than the BMW bracket, but still, it was not all that difficult to remove the support from this piece. So it was not all that painful. So back to this original slide. Hopefully you can see why these parts are good attributes here, between the organic design, the lack there of support, and then just some of the value of, say, these internal passageways, the conformal cooling of some parts that are being produced, the internal air cooling passageways of some of the parts being produced here. So these are some parts that are examples of parts that are traditionally manufactured into an additive process. So we have a bracket here that was redesigned and able to print in metal additive. Significant weight savings, significant performance increase for this particular part. Same thing with this part. You can see that it looks much lighter part. It's going to be as strong, if not stronger, due to the topology optimization, but still quite a bit of weight saving. This part actually here is a part produced for SLM by SLM. You can kind of see inside that this part is stopped midway, but you can kind of see some of the support material inside there and how that support material will need to be removed. But we produce these for SLM 500s because DN40 4-into-1 fittings do not exist, so we created them and build them ourselves. And then that bracket from earlier from the Dassault Systems video, here it is being milled solid and then being built and 3D printed in additive. So that is the end of my presentation. I just wanted to let you know that we are going to be at IMTS. We are in the West Hall, booth 43-2304. Please come by, take a visit. We're going to have our brand new SLM 280 with permanent filter and PSV, which is automatic powder sieving system. We will also have a part, the 30-inch titanium fan blade, built on our SLM 800. It is the largest titanium piece printed in metal powder bed right now. As far as height, it's a very impressive piece to see up close. We're going to do additive designer demos as well. So it's our new software replacement for Materialize that we've produced in-house. And really hope to see any of you guys there. Also, we're going to go over some questions here, but if you have any questions in person, I'll be there as well. Please stop by and say hello. So summary, 7 attributes. Size, does the part fit? Material, does the part weld? Economics, does this part make sense for metal powder bed? Performance, can we meet the performance of the part required? Qualifications, can we make this part, are we allowed to make this part in metal powder bed? Design, will it work, or was this part designed specifically for metal 3D printing? And then post-processing, is this painful to produce? Thank you very much.
Excellent, Kyle. Thank you very much for that great presentation. One question I have for you, Kyle, that a couple people have asked me about: will you be able to make this presentation available as a PDF if people email you and ask for it?
Everything on here should be available. Obviously, we'll have to condense it down a little bit, maybe remove some of the videos and just include links. But yeah, we should be able to provide this as a PDF.
Okay, great. Do you have a slide that has your email address on it in case people want to get in touch with you? And then we do have several questions.
The slide up right now in the middle of the screen is right there.
Oh, there it is. Okay, Kyle.Adams. Okay, so if people want the presentation as a PDF, excuse me, go ahead and email Kyle later. So several questions for you. We'll jump right in. What data is available to validate to regulatory agencies such as FAA that parts made with this process will be as strong or stronger than the typical cast or machined part?
So that's a very good question, and right now there's no solid answer. Because of the metal powder process and how each geometry is different, essentially we need to go through qualification processes, and I assure you there are parts flying right now, so it is being done, but it's a very extensive process where the machine needs to be qualified, the process needs to be qualified, the material itself needs to be qualified, sample parts need to be made, tested, testing samples per build need to be produced for each part. Powder lot traceability all needs to be handled. We do have customers who are doing this right now, so we do understand the process of doing that. If somebody wants to get into that, we can obviously talk more about it later, and based on a particular use application, figure out the best way to do FAA qualifications.
Good, thank you. Is that hipping process done to increase density, which I think it is, right? So what are the typical densities in aluminum before and after the hipping process?
So typical densities are always 99.8 and higher. We like to say if you see 99% even, that we have a problem and we'll go looking for a solution. That being said, with the hipping process, there are certain applications and development work right now in titanium where forced porosity is put in to break up grain structures, and then hipping is used to close up any of those porosities after the part is made, making a stronger piece. So sometimes hipping is used as a tool to create even stronger metal with on-purpose porosity. But after hipping, everything should be 99.9 and above density.
Okay, good. So you showed a couple of examples of automotive parts, the BMW roof bracket and the Bugatti brake caliper, which you would categorize those as lower volume. When would you expect that the metal AM parts would be on higher volume cars?
Well, I would suggest probably in the next 3 to 5 years, you'll start seeing more and more. I know GM just announced that they're putting a seatbelt bracket into a high volume production vehicle. I believe it's their Volt or one of their EV vehicles. Okay. So next 3 to 5 years, I would suspect that a lot of pieces are going to start showing up additive in key places.
Very good. So obviously another key component to successfully transitioning parts or making parts with metal additive is designing for additive. Where is the expertise coming for design for additive? Does SLM offer that service? Are we seeing more colleges graduate designers with expertise in metal AM? Do you want to kind of share your perspective?
Yeah, so there are definitely a handful of universities with design for additive courses. A lot of the work I know our SLM AG group works with Fraunhofer University and a couple others in Germany that produce a lot of additive parts, and a lot of these parts that we even showed were co-developed there. But it's there are design rules, and that is a whole nother major presentation for another time of design rules for additive. And the thing is, there's no hard and fast rules, because every time we say that there's a rule, somebody goes around and breaks that rule and does it anyways, and it works. So, right. We're always developing. This is, this isn't machining where it's been around for 100 plus years. This is very infant industry and infant technology where we're learning more and more every single day, and design rules can change from year to year.
Right. Okay, good. Thank you. CT thickness scanning on Inconel 625 and 718. How thick can they scan, and are there other techniques available for parts thicker than that CT scan limit?
That is a question that I don't have the answer for as far as how thick of a material can a CT scanner go through. I don't have one of those, and I would actually I want to know that question myself. I don't know the answer to that question myself, so I'll probably look that up this afternoon.
Cool. Okay. We stumped you. So in terms of time to make parts compared to traditional machining, and obviously that's going to vary based on the part, but using the brake caliper as an example, this person suggests, can you talk about traditionally machining that component compared to 3D printing it and the time difference?
Yeah, so with that particular component, as far as machining it versus, so if that component was cast traditionally, the turnaround time, initial turnaround time, is much faster for additive because obviously we can throw it in the system and run it versus waiting to get a casting done. But once casting is produced and goes into mass production, we kind of lose a little bit of edge because if that part was made, maybe 10,000 of those were made a year, it would have to be cast just because of the time it takes. You know, this is a welding process at the end of the day, and we can only weld so fast right now. But if you said, you know, to answer the question, I guess a little bit more directly, if you said, here is this brake caliper, go make it, I could have that part to you in a week, whereas in a casting or forging, it might be 2-3 months.
Okay. This person wants to know if you only sell machines or do you offer services for making prototypes or small production runs as well?
So we are just a machine provider. If there is somebody who is interested in getting some parts made, we do have service providers all around the country and also all around the globe that if they contact us, either to me directly and I can forward it on, or go to our SLM Solutions US website, we can send out a supplier list, group of people who are service providers that would be able to provide the small production run.
Excellent. Okay. Can the finished AM parts be welded to other assemblies?
Absolutely. It's all welded material. So everything that we are building is, you know, you hold it in your hand, and if you didn't know it was additive, you know, you'd think it'd be a cast or, you know, forged part. And so this is, you know, it is metal. It's solid metal, and so it can be welded to anything once it's out of the system. Actually, let me go back a couple slides and show this cylinder in the bottom right-hand corner. That is actually a forged disc with metal welded on top of it. So the fan blades are all additively grown onto a forged disc.
Okay. That's pretty cool. Okay. Size limitations. Is the 280 millimeter square the largest part that can be made at this point?
No, the SLM 500 is 500 millimeters deep, 280 millimeters wide, and 365 millimeters in Z height. But we have announced that there is going to be a square machine in the next handful of years here. So I know a couple other competitors already have them, but we're producing a square machine, I believe up to like 12 to 16 lasers. So it's going to be a big system.
Wow. Okay. Good. What is the smallest printable internal passage?
Internal passage, I would say we could probably get down to about 100 microns for a passage. If we go any closer than that, we would risk the melt pool being too wide and closing up the passage. for smallest internal feature or smallest actual physical feature, I would say 200 microns. So that's obviously two different pieces. The feature itself would be solid material, would be about 200 microns. The internal passage, we could do about 100 microns or so.
Okay. We still have several questions and maybe about 5 minutes left. We'll try to get through these as best we can. One of your examples showed the tire tread mold, the mold segments. What kind of surface finish do you typically get on those thin-walled tire segments in stainless steel? And the follow-up question, is sandblasting sufficient to achieve mold level surface roughness, or is there other processes used for smoothing those walls?
Okay, yeah, it's actually a great question. So it's about 6 to 8 RA for surface roughness on that, or 6 to 8 microns, especially for the side walls, which can be very smooth. The grit blasting or surface blasting can clean it up a little bit more, but it's not really going to reach a mold level surface finish. But something like electropolishing or something like that would actually produce the surface finish required for a mold level piece.
Okay. What is the recoder time for the SLM 500?
The recoder time for the SLM 500 is about 8 seconds. And that's also, so with each layer, it's only one recoat versus other machines where the recoder has to travel twice.
Okay. I guess my own question would be, is that an area of improvement coming, or has it already been improved in terms of reducing process time? Is recoder technology, something that is being looked at?
To be quite honest with you, our recoders are, we lead the industry in the recoder as far as time frame goes, and as far as powder distribution goes. So there's always room for improvement, but right now with as far as time, we're 40% faster than anybody else just from recoating alone.
Excellent. Okay. Good. So when you're developing the process for a component, I'm trying to read this question. So do the process parameters, the parameters like layer thickness, build speed, etc., are they evaluated separately for each component, or are there standards based on the specs of the machine that you kind of start with each component? I guess talk about how the process is designed.
So with process parameters, SLM Solutions is very different than anybody else, where we offer open parameter sets. So we will give a stainless steel, titanium, aluminum parameter set. Those parameter sets are open and they can all be edited. So we know that the parameters you get might be 90% of the way there for your particular application, whether you're trying to push the limits in size, speed, so on and so forth. And so then development is made on that particular piece with these particular parameters to achieve the best possible results. So everything's open. It's all, you can do development work on them. And, after purchasing the machine, it's new parameters are all free of charge.
Okay. The question is, what percentage of parts typically need post-machining? This person says that he's heard that 85% of AM parts need post-machining. Is that accurate, or?
I would say right now it is, but we're also taking a lot of parts that were traditionally designed and altering them slightly for the additive process. And I believe as additive grows, and as we hit on earlier, additive design grows, that number will be reduced.
Okay. Let's see. Yeah, this is an interesting question. Two different machines need to be qualified separately even, if it's one version of a machine and then a previous version of the machine, they need to be qualified separately. But how about the same version of a machine with two different serial numbers? Do those need to be qualified separately as well? I suppose we're talking about with FAA or FDA, somebody like that.
Yeah, so right now with the FAA and the infancy of metal additive, each individual machine needs to be qualified separately. That's just how the process works right now. There's just not enough data and not enough track record to say, okay, an S1 280, no matter where it is, works for this particular part.
Right. Okay. Do you want to get into manufacturing costs at all, per cubic inch, per pound of metal deposited, that type of thing? Processing costs?
That would be something that if people have questions of, please email me or a sales team, and we can get into part cost based on material and design and time and things like that. That would be something better taken offline. Mostly because, machine cost is fairly consistent, but powder cost is always changing. It's like gas, it can be different from day to day. Right.
Okay. Another question about CT scanning, and I think we're going to wrap things up. We're over our time limit. What is the minimum resolution achieved with the CT scans in a component with walls larger or thicker, I should say, than 1 centimeter? Do you know the resolution of the scans?
Hold on one second. The resolution of the scans for internal features it's actually very accurate. As a number off the top of my head, I don't have right now, but it's accurate enough to find 5, 10, 15 micron voids within metal. So it's a very, very accurate system.
Right. Okay. All right, we're a few minutes over. I want to thank everybody for hanging in there with us, and certainly I want to thank Kyle very much for what was a tremendously informative presentation. And again, thank everybody for attending the program today. We hope you found it to be a valuable experience. Please remember that an archive of the webinar will be up on our website, 3D Metal Printing Magazine's website, within the next day or two. So you'll be able to review what you learned today and perhaps share it with others within your organization. So again, thanks to everybody for attending. Thank you, Kyle, for a great presentation. Everybody, you may close your browsers now and